Chapter 9, Section 3, Solving Problems Using Systems of Linear Equations, Master Level. So this video we're actually only going to go through one problem in different stages, but really what this problem is doing is it allows us to analyze two different kinds of light bulbs. So here we have an incandescent 60 watt light bulb and a 15 watt fluorescent bulb, and we're just going to compare them. So let's begin. So an incandescent 60 watt light bulb sells for 75 cents. It's just written in dollar form, and it costs $0.0072 per hour to operate, whereas a 15 watt fluorescent bulb sells for $4. Part A asks, how much does it cost to operate the 15 watt bulb per hour? The 60 watt light bulb, we know, costs this much per hour to operate. Well, because this is a 15 watt light bulb, it consumes a quarter of the amount of energy that this one does. Or in other words, the 60 watt light bulb consumes exactly 4 times as much energy as the 15 watt bulb. So that means the cost has to be divided by 4 as well. So what we do is we take the cost per hour of operating the 60 watt bulb and we just divide that by 4, because after all, the 15 watt light bulb consumes less. So we divide that by 4 and we get 0.0018, and this is dollars, I'll put in my units, per hour. Part B, for each light bulb, create an equation that gives the total cost, C, as a function of time. So when we say total cost, not only do we have to consider the cost of operating the bulb per hour, we also have to consider the cost of just buying the light bulb, because the 15 watt light bulb, you have to buy it for $4, so it's way more expensive up front, whereas the 60 watt light bulb, though it consumes more energy, is considerably cheaper to buy. It's only 75 cents. So we just need to create two equations that give us the cost for each light bulb as a function of t. All right, so I'm going to begin by creating a couple of let statements so that we know exactly what C and T actually mean. So we're going to let the cost in dollars be C, and let time, in hours, since hours are already mentioned, we'll let that be T. So knowing this, now we can create two equations. I'm going to be consistent with color, so in blue I'm going to create a cost function for the 60 watt bulb. So we know the cost initially is, in dollars, 0.75. That's to start. But then we have to add on how much we have to pay per hour. So this is 0.0072, and then we multiply that by however many hours the light bulb has been running for. So this is for the 60 watt, and for the 15 watt, its cost is $4. So up front you have to pay way more, but the operating cost is only 1/4 that of the 60 watt bulb. So those are our two equations. What is the total cost of running each bulb for 100 hours? Which bulb is cheaper? So first of all, I'm going to do the cost of the 60 watt bulb, and we know that the cost is $0.75 plus the hourly rate, which is pretty small, times however many hours have gone by. Now of course you'd use a calculator for this. There is a picture of a calculator at the top, and it works out to be $1.47. Alright, so let's just determine the cost of the 15 watt bulb. That's pretty easy. We're just going to use the other equation. So that was cost was $4 plus its hourly rate times 100. And if you use a calculator, you will get a cost of $4.18. So if you operate each bulb for 100 hours, you can see that the 15 watt bulb, though it consumes less energy, is still going to cost more in the end, mainly because it costs so much more just to buy it. What is the total cost of running each bulb for 700 hours? Which bulb is cheaper? So we get to do the exact same thing again. And we're just going to use the same equation, but instead of using 100 hours, we get to use 700 hours. So these light bulbs are burning for much longer. And this gives you $5.79. So now let's just work out the 15 watt. Okay, so just to save time, I've already got the result up here. So the cost of operating the 15 watt bulb for 700 hours, given this equation, is a grand total of $5.26. And hopefully you notice that in comparison to the 60 watt bulb, after 700 hours of burning, it's actually a little bit cheaper. Right, so though I didn't actually write it down, okay, in parts C and D, which bulb was cheaper, I'll just make a note that it was the 60 watt bulb that was cheaper after 100 hours, but after 700 hours, the 15 watt bulb became cheaper. All right, at what point does the 15 watt bulb become the better bargain? Well, before we try and answer that, what I'm going to do is, well, first of all, point out I've just rewritten both cost functions, C as a function of T for both bulbs, and I'm just going to give you a rough sketch as to what the graphs of each one would look like, because they actually are written in slope-intercept form. We're just working with some decimals. So if I want to graph the blue one, the y-intercept has to be below this one because 0.75 is less than 4. Yet this slope is positive, but it is bigger than this one. So when I draw the blue line, I have to draw it steeper than the red. So here's the blue. This is just an estimate. It goes up like this. But then the red one, the y-intercept has to start above here somewhere, but it's not as steep. Okay, so the graph might look like that. Now, when we first worked with 100 hours, we saw that the cost of the 60 watt bulb was quite a bit less than the 15 watt bulb. And if you look at the picture, okay, earlier on in time, the blue one is below the red one. But at 700 hours, the cost of the red was below the blue. So at some point here it had to switch. So really what we need to find is this point of intersection, because it's when the costs are exactly the same we can actually determine at what point the 15 watt bulb actually became cheaper. So let's make a note of that. Right here, this point in time, right there, that's what we're trying to find. Okay, so we have a system of equations, and we could use elimination or substitution. I think I'm going to use substitution because actually in both equations I have a variable that is already isolated. So let's do that. All right, so let's substitute the blue equation into the red one, and I'll keep the colors consistent. So I'm going to replace this C in red with this up here in blue. So that means 0.75 plus 0.0072t. That is equal to 4 plus 0.0018t. Okay, so I've eliminated the c's, and all I need to do is isolate and solve for t. All right, so I'm just going to solve for t. I'm going to collect the t's on the left and just the plain numbers on the right. So I'm going to subtract 0.0018t from both sides. Now remember, you can use a calculator. So that will give me 0.0054t equals, and I'm going to subtract 0.75 from both sides. So that's going to give me 3.25. And to finish off, I will just divide both sides by 0.0054. Okay, without a calculator this could be a little bit painful, so by all means we can use one. I'm just going to run out of room here. So I'll just move over here. And I'm going to get an ugly decimal. Remember, t is in hours, so I'm going to round it. So 3.25, I get approximately, so I'm just going to put a little dot here. That means approximate. Approximately 602 hours. Okay, so this time of 602 hours, that is the time at which these two lines intersect. And that should make sense because that is between 100 and 700 hours. And we know somewhere in between there they had to cost the same because After 602 hours, the 15-watt bulb actually became cheaper, and we saw that one here. Normally we want to actually solve the entire system, so we'd actually want to find the cost as well, but the question doesn't ask for the cost. It just says, at what point does this bulb become cheaper? Well, they're implying time. Okay, so after 602 hours, roughly, of burning the light bulb, the 15-watt bulb becomes the better bargain.